Good morning. Today we're going to learn how to write a formula and to solve for a maximum volume for a rectangular prism. So we're going to first just do a quick warm-up. This is on page 163 in your workbook. So if you pause the video while everybody gets their workbook out and goes to page 163. So we have a cocoa company, and it sells its cocoa in a rectangular prism-shaped box that measures 5 by 5 by 6.25 inches. The company would like to redesign its packaging so that the box is a cylinder with a diameter of 5 inches that holds the same volume of cocoa as the prism-shaped box. So we've got a box. So we've got the box, and now we want to have a cylinder with the same volume. So remember, a 5 by 5 by 6.25. So 5 by 5 by 6.25 has a volume. We don't know what the volume is. So we need to solve for the volume, or we need to find the volume of this box. So find the volume of the prism-shaped box. Well, we know volume is going to be the area of the base, which is 5 times 5, which is 25, times 6.25. So this volume is going to be equal to 156.25. What equation can we use to find the height of the cylindrical box? Well, we know we want a diameter of 5. The company would like to redesign its packaging so that the box is a cylinder with a diameter of 5 inches. So what equation can I use to find the height of the box, of the cylinder? Well, we know the volume of the cylinder still has to be the same. So it has to be 156.25 cubic inches. And we know the volume of a cylinder is the area of the base, which would be pi r squared. So half of 5 is 2.5. 2.5 squared times pi. So 2.5 squared times pi. And we get 19.63. So the area of that base is 19.63. So the only thing we don't know is the height of the box. So there's your equation. Now how can I solve for the height of the box? Well, I would just divide by 19.63 on both sides. So take 156.25 divided by this number. You can just use your cursor and copy and paste that number. And you get, excuse me, 7.9, and it said round to the nearest hundredth. So this 5 gets rounded up to 6. 7.96 inches. So the height of that cylinder would have to be 7.96 inches in order for it to have the same volume as the box. Okay, just a quick reminder, and these aren't on your paper, on your notes, so you can just think about it. This is old, very simple writing equations using symbols from the words. So when 6 is added to 4 times a number, the result is 50. Find the number. So remember the keywords. When 6 is added to 4 times a number. Well, when we're adding, we're using addition. And 4 times a number, well, that a number is our clue that that's our x. So 4 times our x. And then 6 is added to that. The result is, so that's your keyword for your equal sign, is 50. Solve for that by subtracting 6 from both sides and divide it by 4, and you should get x equals 11. The second one, the sum is again addition, of a number and 9. So our number is being added to 9, x plus 9, is multiplied by So this sum is multiplied by -2. So when it says the sum of a number and 9 or a number and another number is multiplied, you have to use your parentheses for that sum and then put the number on the outside. And the answer is -8. Find the number. So I have -2x minus 18 equals -8. -2x equals, if I add 18 to -8, I get 10. So our x is going to equal -5. On an algebra test, the highest grade was 42 points higher than the lowest grade. Well, if it's 42 points higher than, then that means we're adding 42 to the lower grade. The sum of the two grades was 138. Subtract 42 from both sides, and you should get 96. So that person got a 96. Okay, so we're going to skip this problem and go to this one, because this one is on your paper. So we've got our rectangular piece of cardboard, and it's 15 inches longer than it is wide. If 5-inch squares are cut from each corner and the remaining piece folded up to form a box, the volume of the box is 1,250 cubic inches. Find the dimensions of the piece of cardboard. So remember, dimensions are, we've got 3 dimensions because it's a cubic, or it's a rectangular prism. So we have length, width, and height for dimensions. That's that word that sometimes we're not sure what it means. And then you've got a rectangular piece of cardboard. So I'm going to draw my rectangle. We always need to draw a picture for these. It's 15 inches longer than it is wide. So if I know the width is x, 15 inches longer than x would just be x plus 15. If 5-inch squares are cut from each corner, so now I'm cutting out corners. And then they're going to be 5 inches on both sides because it said they're squares. So each of these is 5 inches all around. So I cut out 5-inch squares. The volume of that box is 1,250 cubic inches. Well, I know that my base, use a different color here, it's going to have different dimensions than the original box because I cut out 5 inches from each end. So the area of the base is going to be this number, or this length, times this length. Well, if originally the whole thing was x, but I took 5 inches, here I'm going to put this, took 5 inches off of that on each end, I took 5 inches off of that on each end, I'm taking off 5 inches here and 5 inches here. The new dimension is going to be x minus 5 plus 5, which is 10. And what about the new length? Well, if I take 5 inches off of each end of that, I'm taking 10 inches off. So this is going to be x, if I take 10 away from 15, x plus 5. So I know the base is going to be x minus 10 times x plus 5. Well, what would the height of this new box be? If I take 5 inches off and I fold this up, this length right here is going to be the height of the box because that's how high it's going to go. So the height or altitude is going to be 5 inches. So the volume, if I write a formula for volume, we know the volume is 1,250 inches. That's going to be equal to the base times the height. So let's multiply the base out. We get x squared. I wrote that wrong. X minus 10. X squared minus 5x minus 50. And that's going to be multiplied by the height, which is 5. Well, I noticed that this number is a multiple of 5. So if I divide both sides by 5, I can get this down to a more manageable number. So let's divide that by 5. 1,250 divided by 5. And that comes to 250. So I have 250 on this side equals x squared. Now the 5's are gone on this side because that equals 1. X squared minus 5x minus 50. Okay, I need to get that 250 over the other side because I need 0 on this side. So minus 250 minus 250. So I have 0 equals x squared minus 5x. And if I have negative 50 minus 250, that's negative 300. I could use the quadratic formula, but I'm thinking I might be able to factor this because I think I need factors of negative 300 that add up to negative 5. And I know 30 times 10 equals 300, but that won't give me a difference of 5. Well, let's divide this in half. 15, and that would be times 20. Well, those two numbers do have a difference of 5. So I have x, 15 and 20. Now I need the sum to be negative, so that 20 needs to be my negative. Okay, so that equals 0. Well, if I set both of these equal to 0 and solve, I'll get negative 15 and 20. Now remember, we're looking for dimensions of a box. Our dimension can't be a negative number, so we can't use that negative 15. So that means the x, or our width, is 20. So the width is 20. We already know the height was 5 because that was given to us in the problem. How do I get the length? Well, the original is it asking for dimensions of the box or of the cardboard? Cardboard. We want the dimensions of the cardboard. So x plus 15. So the length is 20 plus 15, or 35 inches. Dimensions of the piece of cardboard. So this is not the problem we're going to be doing today, but this is kind of an intro or a warm-up to how to do the problem. We're just going to focus on one maximization problem today, and that is going to be in your notes in just a minute. So we're going to talk about surface area of a rectangular prism. We're going to skip the surface area for today. We're going to go right to the problem that we're going to do. So an optimization problem seeks to maximize or minimize some quantity. In this case, it's going to be volume. And so, for example, you may want to maximize the volume of a box, like the one we did for the warm-up, from a given amount of cardboard, or minimize the surface area of a tin can. We're just going to focus on the box today, just because this is kind of a new concept for you guys, and I want you to get this down. So an 8.5 by 11 inch piece of cardboard is made into a box with no top by cutting congruent squares from each corner and folding the sides up. What are the dimensions of the box with the largest volume? Okay, so dimensions, we're talking about length, width, and height. So what are the length, width, and height of this box? First thing you always do when you do one of these is draw a picture. So first of all, what does my box look like? There's the box. And we don't know what the length, width, and height are, but we've got kind of a picture of what our box looks like. And we have our piece of cardboard with the sides cut out. So I'm going to draw the cardboard, then I'm going to erase the corners. We've got the corners cut out, remember? I know that's going to bug somebody, so I'm just going to fix it now. Okay, so now we've got our picture basically drawn, but what about the labeling part? Well, I know I cut X out of the corners, so this length here is X, this length here is X, all the way around. So I know the height of the box is X. I know for sure my height is X. What do I know about these side lengths? Well, I know they started out 8.5 by 11. Oops. So what would the new length be? The length and width be after I cut out the sides, the corners, I mean, and made the box. Well, if it was 8.5 and I cut x and x out, well, 2 times x is just 2x. So this is going to be 8.5 minus 2x here. And then what would this one be? Well, I'm cutting the same amount out, so it'll be 11 minus 2x. And that will be this part. Okay, so I know that our new length and width are 8.5 minus 2x and 11 minus 2x, and the height is x. So width, length, and x is your height. Now we have to determine what we're trying to maximize. We're maximizing, either maximizing or minimizing. Okay, we're going to maximize volume. So volume, remember, is the area of the base, which is the length times the width, times the height of the object. So write a polynomial for that quantity in terms of one of the variables. Well, we only have one variable that we're working with here, so it's kind of making it easy on us. The only variable we're working with is the x, which is your height. So the volume is the height, which is x, times the length, which was 11 minus 2x, times the width, which was 8.5 minus 2x. And you don't have to multiply that out. You're going to just leave it like that. Now we need to think about what would be the domain. What are the possible values of x? Well, we know it can't be anything less than 0, so x has to be greater than 0. What about the range? I mean, what about the maximum x value? Well, if the shortest side is 8.5 inches long, and I cut more than half of that out, I wouldn't be able to make a box. So it can't be more, the highest x value can't be more than half of that shortest side. So half of 8.5 is 4.25. Okay, so what would the volume be if x is just above 0? Well, if x is 0, the lowest y value is 0 also, right? So this is the domain, this is the range. I'm writing it a little bit different because you're going to see why in a minute. So I know y has to be greater than 0. What if x were 1? The least amount I'm going to be able to cut out, 1 inch. That would give me the highest number here probably. Well, let's make it 1. 11 minus 2 times 1 is 9. And then 8.5 minus 2 times 1 is 6.5. So 9 times 1 times 6.5. Approximately 59. So let's just put in, let's go a little above that and make it about 75. So once you get that ballpark number, just go up a little bit from there. And you're going to see why when we have to put this in the calculator. So we have steps for putting it in the calculator. You're going to graph the function and find the maximum on the graph. The maximum or the min. In this case, we're just doing maximum. Okay, so on the back of your paper, you have or below this, you have the steps for this. So putting it in the calculator, let's go to your y equals menu, and I already have the function entered in here. So it's x times 8.5 minus 2x times 11 minus 2x. I put it in backwards from the way we wrote it. That's fine. It's still going to graph the same way. And now you want to look at that domain and range. So you want to press the window key, and we want to set our minimum x value to that lowest number in the domain, and then we want to set our highest x value to that highest number in the domain, which was 5. Well, 4.5. We're just going to go a little above that. Leave this x scale at 1. And then your y minimum is again 0. And then we put 75 for our maximum y. So now you're going to just, you're going to press graph. And if you don't want that, the double screen, remember you just go to mode and arrow down to make this full. So press or highlight the full. And then press graph. Okay, so we want this number here, whatever it is. We want to know what that is. So we're going to tell the calculator to find that. You hit second trace, and we want maximum because we're looking for that maximum. Now here's what you need to do to set the bounds. There's going to be a left bound and a right bound. So we want to set a bound to the left of this point and to the right of this point. And we're basing that on the x values. So we want the x value to move over to the left. So you can either put in a number there, or I'm just going to use the cursor to move that spider to the left. It doesn't have to be very far, as long as it's to the left of that point. And so the calculator puts a bound to the left, and you do the same thing to get it to the right. And then press enter. So we've got two boundaries on the left and right. And again, notice mine aren't perfectly symmetric. It doesn't have to be. It just has to, you just have to have your bounds surrounding the point you're trying to find. And then you just tell the calculator to guess by pressing enter. So my maximum value is my maximum x value is 1.585. So remember, x was the height. And then the volume at that height is 66.148 cubic inches. So the volume is 66.148 cubic inches. And the height at that, when it's that volume, is 1.585 inches. Now to find the other two dimensions, we just plug that 1.585 in for x. So the length is going to be 11 minus 2 times that number. And the width is going to be 8.5 minus 2 times that number. And if you put those in your calculator, you will get, for the length, you'll get 7.83 inches. And for the width, you're going to get 5.33 inches. So the question was, what is the largest volume and what are the dimensions? So there's our answer. Okay, so you're going to go to page 163 in your book, and you're going to try exactly what we just did. The problem is almost exactly the same. Not 163. That was your that was your warm up. You're going to do problems 1 through 3. It's all based on the Letitia problem. It's on page 167, number 1, 2, and 3. That's all I want you to do today.